to see that this claim is true, that every formula can be written in disjunctive normal form. And then there is conjunctive normal form, which is just the same, except that you switch and or. So it's a conjunction of disjunctions of that form. Okay, so that is one useful thing to know. Let me see. All right. No, I didn't see any more questions at the moment, so I'm going on. But as I said, feel free to raise your hand at any time. So here's another thing which is very useful to know and is an important part of propositional logic. It's truth functions. And again, that's mostly in the exercises where it is spelled out with various hints of how you can prove these things. So what is a truth function? It's a function from truth values to truth values, but it can take one or two or three truth values as arguments, and it gives a truth value as the value. So if you take unary truth functions, there are only 4 of these, because you can map 1 to 1, or you can map 1 to 0, and you can map 0 to 1, or you can map 0 to 0. So those are 4 possibilities. Those are the 4 unary truth functions, and we already know one of these, namely negation, which is switches between 1 and 0. That's one of these truth functions. If you take binary truth functions, then there are 16 of these, and conjunction, disjunction, implication are or denote 3 such truth functions. So conjunction, for example, it denotes the function which takes 1, 1 to 1, but all the other 1, 0, 0, 1, or 0, 0, all those combination it maps to 0. So every truth table expresses a truth function, and vice versa. But those are binary truth functions. Then you can have truth functions for ternary truth functions with 3 arguments. How many of these are there? Well, it's easy to calculate that there are 2, let's see. There are 2 to the 8 times 2 to the, no, 16 times 16, yes, 144 possible ternary truth functions. We don't have any symbols for these. We could have introduced connectives that take 3 arguments, but we don't. Why don't we do that? Well, because what we have is already enough to express all truth functions, and that's the statement here on the bottom, the final statement on this slide. Every n-ary truth functions for any n can be expressed by a formula in propositional logic which has precisely the letters P1 to Pn. That is to say that propositional logic is truth functionally complete. It can express every truth function. That's why we don't need more than the more connectives that the ones we already have. And in fact, as you have seen, we can skip even some of these because for example, implication can be defined in terms of conjunction and negation, etc. Okay. Maybe there will be a little bit of homework dealing with these truth functions. I want to end the discussion of propositional logic by giving you an example of a proof by induction. So it proves an important fact, but it also an example of a not completely trivial but easy proof by induction. So it's the first such example that I will go through. So let's first see what the claim is. The claim is about replacement. So you have a formula, and in that formula there are various sub-formulas. There are propositional letters, for example, and you can replace such a propositional letter by another formula. And I've indicated here a notation for that. So phi p with square brackets means that there may be some occurrences of p inside phi. Phi is a complex, or phi is a formula, and it may have some occurrences of p. And then I write like this. I replace p in the square brackets by psi, and that's the result of replacing those particular occurrences of p by a sentence, psi. I'm not requiring that there actually are any occurrences. So if there is no occurrence of p in phi, then nothing happens, right? The result is phi again. So that's just notation for replacing a sub-formula with another formula. Next thing, for the formulation of this claim below, I will use valuations not only of the propositional letters, but of extended to all the formulas. So V of theta is the value of, oh sorry, that's a misprint here. It should be not phi, but theta. So it's the value of theta under the valuation V. So the value is 1 if theta is true in V, and it's 0 if theta is false. Then I can say the following. This is the theorem. If V phi is equal to V, sorry, start again. If V psi is equal to V psi prime, so they have the same truth value, true or false, under the valuation V, then the truth value of phi of psi, phi which has psi in it, is the same as the truth value of phi when you replace psi by psi prime. So this talks about particular truth values, but the form in which this is mostly used is the corollary here, which is written in the textbook as a lemma 218. And the lemma says that if psi and psi prime are logically equivalent, so they are true in the same valuations, then the same holds for phi and phi where you have replaced psi by psi prime. And if you think about it, this is something we do all the time. So for example, I said that, yes, go back to these equivalences. Here are some equivalences, and I said we can use these equivalences to simplify or to reorganize a formula, and for example, bringing it to one of these normal forms. But that means precisely that you have some sub-formula and you replace it by another sub-formula which is equivalent to the first, and you take for granted that this is fine, that the result of that replacement has the same truth conditions as what you had before. And that's exactly the case, but that is what this corollary says. So it's a corollary that one uses it's a fact that one uses all the time about replacement. But if you are careful, you would like to prove this fact. So there are various ways to prove it, but I will go through now one way of doing it. Another way is indicated in an exercise. Okay, so here is the claim on top again. We take a particular valuation V, and we're assuming that the value of psi is the same as the value of psi prime. And we have a formula phi, and then we have psi occurring in it, and we replace psi by psi prime. And the claim is that the value of these two is also the same. We're doing this by induction on phi. So we're saying that phi, every formula phi has this complex property, which is written on the first line. So really, if we were extremely careful, we would say, what is the property of phi we're talking about? Well, the property is this. For every valuation V and every psi and psi prime, such that psi and psi prime have the same value under V, it holds that the value of phi, where you have replaced P by psi, is the same as the value of phi, where you have replaced P by psi prime. So that's a long description, but that is the property we're talking about. It's a property of phi, and we want to show that it holds for every phi, so we show that by induction. So there are various cases. First, we want to look at the case where phi is an atom or a sentence letter. Okay, so now case one, phi is an atom. Well, there are two subcases. The first one is that it's an atom, but it's not P. Remember that I said that phi may contain occurrences of P, but I'm not requiring that. So it could actually be another, even if it's an atom, it could be another atom than P. It could be Q. Well, in that case, the claim is clear because nothing happens. Replacing P by psi in Q doesn't change anything. You still have Q because there are no occurrences of P to replace. And similarly, replacing P by psi prime also changes nothing. You still get Q. So you have the same formula Q in that case. So that was the first case, the first subcase of case one, which is phi is an atom, but it's not the atom P. Okay, the second subcase is that it is the atom P. Well, then you see on this line here that on the next line, so phi is P, and what is the result of replacing occurrences by P by psi? Well, the result is precisely psi. So P square brackets psi is psi. But now we already assume that the value of psi is the same as the value of psi prime. which and psi prime is the result of replacing. Oh, there is again a typo here. So let me correct that.